power AC circuit lesson 6. To solve the problem in low voltage AC circuit. So the power AC circuit. At the end of this lesson, students should be able to calculate the value of power triggers, draw and label the power triggers for the AC circuit, draw circuit diagram showing the 1 meter connection, measure the true and apparent power. So this is the power trigger. So this angle is an angle, theta is an angle between voltage and current. This one is a S equal to VI apparent power. This one is a reactive power Q. Q is a VI sine theta or S sine theta. Here horizontal is a real power P, VI cos theta or S cos theta. So the S is a S angle Q. Power factor lambda is a P by S. P is a real power divided by apparent power. So theta is often called the power factor angle because it related to the real power to the apparent power. So in this case, we do the power triangle. This power triangle S equal to VI, P equal to VI cos theta, Q equal to VI sin theta. So in this case, a pure resistance circuit, P equal to VI, Q equal to 0. So in this case, this is a circuit voltage diagram is a voltage is a pink and the current is a blue. So real circuit, pure resistance circuit, voltage and currents are in phase like this. And power will be the black one. Power is a the diagram. Power graph is that one. So in this case, our real power triangle. So P equal to VI cos theta. In this case, Q equal P equal to 0, Q equal to minus VI. So this is the voltage diagram here. And this is for the real inductive circuit diagram. So current is like this. Current left the voltage. Current left the voltage by 90 degrees. So in this case, our real power is 0 and Q equal to minus VI. So this is for the apparent power, reactive power. And here power is like this. The Q equal to S is there, real power is that this blue down. So the predicate inductor has a standard system, therefore use the standard real power I square R. Inductors are used in the AC circuit because they are very little real power. So this is for the inductive circuit diagram. And for the power capacity. For the capacity, real power 0, Q equal to VI. This is the voltage circuit. So in this case, S equal to VI, Q equal to VI sin theta, P equal to VI cos theta. So this thing is the voltage diagram. And this is the blue is the current graph, current is the voltage, and power is like this. The power graph is Q equal to S, the power graph like this. So the way to draw calculate this problem, a single phase 20 ampere load has the power factor 0.866 when connected to the 240 volt 50 Hz supply. Determine the circuit phase angle, apparent real and reactive power of the load. So what do we know is that we know the current is 20 ampere, power factor 0.86 lagging, voltage is 240 volt, frequency 50 Hz. We have to find out the Q, S, P, and theta, S, P, and Q. So the P equal to VI cos theta, Q equal to VI sin theta. So S equal to VI. This diagram here, Q equal to minus cos lambda. So Q equal to minus 30 degree, S equal to VI. S equal to 20 minus 240, so the 4/8 kVA. P equal to VI cos theta, P equal to 4/8 multiplied 0.866, so the 4/16 kilowatt. So the theta equal to the square root of S square minus P square, or theta equal to the Q equal to VI sin theta. So 4/8 multiplied minus 0.5, so 2/4 kilowatt. This is the answer. The next problem is single phase 240 volt 50 Hz supply connected to the small battery. If the total current drawn from the supply is 30 ampere with a lagging power factor of 0.7, determine the power dissipated by the load, the reactive and the apparent power, and the drawn power cycle. So what we know is that we know the currents are 30 ampere, power factor 0.7 lagging, voltage 240 volt, frequency 50 Hz. We want to know that P equal to VI cos theta. So the P equal to 7/2 kilo multiply 0.7, you got the 5.04 kilowatt. So this is a 5.04 kilowatt is a real power. And you equal to VI sin theta. So theta is to minus cos inverse, so this is a minus 45/7. So Q equal to VI sin theta, so the 7/2 multiplied 7.14 minus, so you got the minus 5.14 kilowatt. So this is the reactive power. H equal to VI, so that this H equal to VI. This gap, the angle will be the 45.57 degree. So the H equal to VI, so 30 minus 240, you got the 7.2 kVA. So this is for the 7.2 kVA. So load 1 is a 5.04 kilowatt, 0.7 lagging. Load 2 is a capacity load, 1.92 kVA. Load 3 is a pure resistance, 2.4 kilowatt. And also the source is a 240 volt 50 hertz. We have to draw the power trigger and find the current. So the another thing is a load 1 is a, in this case, a 5. So this is the PS a 5.04, 0.7 lagging. And so it's S equal to P by lambda. So the 5.04 divided by 0.7, so the 7.2 kVA. Minus theta is a minus cos about 0.7, so minus 45.6. So the minus 45.6 degrees. And then we draw the power trigger like this. So this way we draw it. Similarly, we draw the capacity load. In this case, that if we connect the capacity load, then we power trigger like this. So there will be the reactive load, capacity load, and the pure resistance load. Power today is you add everything, so 7.4 kilowatt. And reactive load is a 3.22 this angle, so that we find out the S, so square root of 7.4 square plus 3.22 square, so 8.11. So Q is 1.92 minus 5.14, so minus 3.22. P is 5.04 plus 2.4, 7.44. So theta have to find out. So that this is the reactive power divided by active power, so minus 23.4 degrees. So this is lambda angle, you also get it. I equal to S by V, so the 8.11 angle minus 23.4 by 240, you got the 33.8 angle minus 23.4 degree. So this is that we have to do that thing. Next one, power factor improvement. So power factor improvement. So at the end of this lesson, students should be able to determine the power factor of this single phase circuit, state the effect of low power factor in the single phase circuit, determine the value of capacitor or the rated power required to improve the power factor, state the requirements concerning the installation power factor. So this is the power triangle. So this angle between voltage and current is a phase angle. So this is the apparent power S equal to VI, S equal to S angle theta, and real power P, so VI cos theta. So theta is a reactive power Q, the VI sine theta. Cos theta is called the power factor lambda of the circuit related to real power to the apparent power. So the power factor lambda is cost measure of the installation efficiency. So lambda is cos theta, theta is a phase angle of the circuit. Low power factor can caused by the inductive load, lagging power factor, fluorescent light, bolus, or high light leads are loaded motor and transformer. This is for the low power factor. Capacity load is a leading power factor, so this is long period run. The low power factors can cause an increase of the current I square R loss, increase the cable size, increase equipment cost require a higher rating, increase the generation cost. Also, the operational problem can happen. So this is the effect of the low power factor. Therefore, we have to do this power factor improvement. Use of service installation rule require the consumer installation should have the power factor not less than the 0.9 lagging, and the power factor of the any installation must not become leading at the any time. So this is a power factor improvement. Use of service installation rule. How can we improve the power factor? Lambda equal to cos theta. So the P equal to the power trigger is angle theta here. So that we have to reduce the angle. So that will be the reduce the Q. Reduce the reactive power, we can increase the power factor. So, but this reduces the S and P, but does not change the real power P. More reactive loads are the inductive load, therefore the lagging power factor. Counter at the inductive load, in this case we have to connect the capacitor in parallel. Okay, so we have to see the problem. A 240 volts or 50 hertz single phase installation, draw the 40 ampere from the supply at the power factor 0.4 lagging. Determine the farthest region of the capacitor bank to be connected in the parallel with the load to achieve the installation power factor of 0.86 lagging and unity. So what do we know is that we know about the 240 volts supply, voltage 240 volt, frequency 50 Hz, current 40 ampere, the power factor is a 0.4 lagging. So we want to know is that we have to know the capacitance. We have to calculate. So the theta equal to cos inverse lambda, so the cos inverse 0.44, 0.4, so 0.6.4. So this is the angle 6.4 degree. And so voltage are 240 volt, current 40 ampere, so S equal to VI, 240 minus 40, so the 9.6 kVA. And so we got to VI cos theta, so 3.8 kilowatt we draw, and we draw the Q equal to VI sine theta. So 9.6 minus 0.9 minus 8.6 kVA. So we have to find out this angle. So 0.86 lagging, we want it. So the 0.86 lagging, we have to find a cos inverse, you got the 30 degree. So this 30 degree, we draw it. And so you got to S sine theta. So the S equal to P by lambda, so the 3/8 divided by 0.866, so 4/4 kVA. So then in this case, 4/4 multiplied by 0.5, so 2/2 kVA. So in this case, QD equal to 2 plus QC, so the QC equal to QD minus QL, so the minus 2/2 plus 8/6, you got a 6/4 kVA. So this is the way. So QC is 6/4 kVA. Then the QC equal to VC into IC. So the voltage is a 240 volt, frequency 50 Hz, I is equal to VC by HC. Or the Q is equal to VC squared divided by HC. So the V squared divided by QC, so 240 squared divided by 6/4 K, so 9 ohm. H squared to 1/2 by FC. C equal to 1/2 by FHC. So the 1/2 pi into 50 into 9, you got the 353.7 microfarad. So this is a calculation. So the to get the unity power factor, voltage got 240 volt, frequency 50 Hz, lambda is equal to 1. So in the cos inverse 1, so 0 degree. So S equal to 380 divided by 1. So P by power factor, so 3/8 kVA. So the QD equal to the QS minus 8/6 kVA, QD equal to 0 kVA. QC equal to 8/6 kVA. So the Q equal to 8/6 kVA, H equal to V squared by QC. So 240 divided by 8/6, you got the 6.7 ohm. And then you also see the H equal to 1/2 by FC, so 1 by C equal to 1/2 by FHC. So 1/2 by into 50 into 6/7, you got a 475.3 microfarad. So the A240 volts are 50 Hz single phase installation, draw the 10 ampere from the supply, power factor 0.6 lagging. Determine the farthest region of the capacitor bank to be connected in parallel with the load to make it comply with requirement of New South Wales service installation rule. What do we know is that voltage of 240 volt, frequency 50 Hz, I is to 10 ampere, lambda 0.6 lagging. We want as a lambda 0.9 lagging. What do we want to know is that we have to know the capacitance. We have to calculate, in this case, voltage 240, frequency 50 Hz, current 10 ampere, and power factor 0.6 lagging. These are the cos inverse lambda, so the 53.31 degree, and S equal to VI, so 10 into 240, 2/4 kVA. P equal to VI cos theta, 2/4 into 0.6, 1/4 kilowatt. Q equal to VI sine theta, 2/4 minus 1.8, minus 1/92 kVA. So this is the things how we draw the real power, reactive power, and apparent power. Theta equal cos inverse lambda, so cos inverse 0.9, so 25.8 degree. And then Q equal to S sine theta, so S equal to P by lambda, 1/4 divided by 0.9, so 1/6 kVA. The Q equal to 1/6 into 0.44, so the minus 0.7 kVA. Q equal to QL plus QC, so the QC minus QD minus QL, so the 0.7 plus 1/92, you got a 1/22 kVA. So that we also have to calculate H equal to V squared by QC. 240 divided by 1/22 K, so the 47.2 ohm. H C equal to 1/2 by FHC, so the 1 divided by 2 pi into 50 into 47.2, you got a 67.4 microfarad. So that the next one is a 400 volt 50 Hz fluorescent lighting load in shopping center is measured at the 6,000 watt and the power factor 0.26 lagging. We have to determine the kVA rating of the capacitor bank to improve the power factor to 0.8. Use both the measurement and the calculation method. So firstly, we also have to calculate the determine the current through the capacitor bank. See the determine the capacitance value of the capacitor required. So we have to start the draw the diagram. 400 volt 50 Hz, in this case power, real power 6 kilowatt, power factor 0.26 lagging. And then we have to find out that this is a KVR band. So this is the KVR band here. Power factor. So in this case, we draw the this diagram. The total current IT and current flow to the KVR band is IC. So P equal to 6 kilowatt. These are going to cause in bar, so the 0.26 of 74 by 9 degree. So the 6 kilowatt 74 by 9 degree. Theta equal to tangent theta Q1P, so the PS tangent theta, so the 6 multiplied tangent 74 by 9, so 22 by 2 is a kVAR. So we draw it this one. 6 kilowatt 22 by 2 kVAR, cos sigma lambda, so the cos sigma 0.8, theta is 36.9. So tangent theta is Q1P, so PS tangent theta. So the way we sit into tangents are 36.9, so 4 by 5 kVAR. So the Q is equal to QT plus minus QL, so that 22.2 minus 4.5 7.7 kVAR. So this 7.7 kVAR need to be reduced. So then we had to calculate the IC equal to QC by VC. So the IC is 7.7 K divided by 400, 44.25 ampere. So H equal to VC by IC, so that 400 divided by 44.25, you got a 9 ohm. So C equal to 1 by 2 by FHC, so that 1 by 2 by into 50. Multiply 9, so you got that 35357 microfarad. The next one is the following meter reading were taken on a single phase circuit. Use these to determine the power factor and the phase angle of the circuit. 1 meter 240 volt and meter 20 ampere, 1 meter 4.2 kilowatt. What do we know is we know about we draw this as 1 meter diagram. So this is a current coil and a voltage coil and a voltage and current connection. This is low. P equal to 240 volt I 20 ampere, P 4.2 kilowatt. We want to know lambda theta. Lambda equal to P by S, theta equal to cos inverse lambda. So we draw the diagram voltage, current, and the power, and the theta cos inverse lambda. P equal to V equal to 2.20, so 4 by 4. Lambda equal to 4.2 divided by 4 by 8, so 0.875. And theta equal to cos inverse 0.875 to 29 degree. So this is the ways how we complete the AC circuit. After that, we have to do this advanced diploma electrical engineering. So we do the electrical diploma 2022. So electrical diploma 2022, we have to see this E303. So that go down here, we do this lesson study option 3. So YouTube video lesson. YouTube video lesson, after that you have to do the transmission like E303. So go down and we find out the E303 transmission line. So E303 transmission line here. So the if you don't highlight computer.com/video lesson